So we have three presentations in this session. The first presentation is by Nar from Chulalongkorn University, Thailand, and they'll present their work on development of network security testbed for abnormal traffic data detection and mitigation and cyber attack analysis using machine learning. Your
Thank
mic
you
is
very much.
mute. Yeah. Thank you.
Do you see our screen?
Yes.
Okay, thank you. Okay,
Welcome.
good morning, everyone. My name is Nam Visalunglod and also Pachapong Thumlongkun. I'm here to present the work on development of network security testbed for abnormal traffic data detection and mitigation, cyber attack and analysis using machine learning.
Can you please unmute your mic? Your mic is mute.
Oh, sorry. Sorry, do you hear me? Hello.
Yes, we can hear you now.
Oh, sorry. Okay. Let
Yes.
me start. Okay. In the present, the cyber attack is becoming more common. This slide is showing some example of the attack such as the ICMP, a UDP, and also a DTP, a SYNCPLUS. Okay, while developing a test-based network, important for studying cyber attack. First, also because the attack is illegal and also ethically problematic, so we need to. So we need the control environment that we can studying it and also giving them the insight so we can counter measure in the real world. This project objective has the three objectives. First we want to detect abnormal traffic volume, indicate of the dot attack, and secondly we want to mitigate the effect of the attack using the SDN technology, and also the third one will be we want to simulate the dot attack for analysis and also testing. Our scope of work in this project, we use Mininet for network simulation and focus on the dot attack at data layer. We simulate attack using the HPing 3.2 and partially implement machine learning for abnormal traffic detection. While machine learning has been well documented in this field, our approach center on combining SDN management with detection capability. This is our test-bed topology. It is like show network emulation setup of our test-bed. In the control plane is managed by the Liu controller. It oversees the decision making and also communication between data plane using OpenFlow protocol. In the data plane, it composed of multiple OpenFlow switch. It handles the actual transmission of data between hosts. In this setup, we have the 18 hosts. The blue one on the left hand side, H1, it represents the server host, and for the red one, H3, H6, H9, H12, H15, and H18, it represents the attacker host, shown in red, and the remaining host is represented in the white. It's a normal user. In this slide, we highlight commonly communication protocol that are used
Recording in progress.
ICMP, UDP, and TCP. And in our study, we will study these three protocols. In this slide, we explore how traffic data is being collected in our test bed. For our machine learning model, the data is we have three main steps. The first one is requesting data every 3 seconds. The new controller send data request to OpenFlow switch to retrieve the flow table data. And the second one is data transmission from the OpenFlow switch send the request for table data back to the controller. And lastly, the third one, data storage. The data is saved as the CSV file. A total of 22 types of data is being collected, but there are some important example. A switch ID, a solid date, destination ID, packet count, byte per second, and packet per second. In this slide, we look at the general data transfer pattern using our testing environment. To create the robust data set, communication is performed over 400 rounds. Each round consisting of 3 different types of data transfer using the following protocol: ICMP ping command, and also the second one would be UDP and TCP iPerf command. This slide is a reminder of our topology. This slide is provide a visual overview of sequence general traffic data transmission during each round of our experiment. In each round, data is transmitted in the following order: ICMP, UDP, and then the TCP. In this slide, we focus on the key parameter that influence data communication during our experiment. For the ICMP protocol, the parameter are packet size and also the interval time between packet transmission. But for the UDP and TCP protocol, primary parameter are bandwidth. In this experiment, we divide our case study into 3 distinct cases, each focused on adjusting the specific parameter. The first case would be we want to adjusting the bandwidth of the UDP and TCP protocol to analyze the impact on traffic pattern. The second one would be we adjusting the packet size of the ICMP protocol to understand how it affects data transmission behavior. And lastly, adjusting the interval time between the packet transmission in the ICMP protocol to observe the change in communication consistency. And in each time, the fixed value is set as the ICMP packet size would be 150 byte. Transmission interval is 2 milliseconds, and the bandwidth is 70 megabit per second. This table is show the output file name. The data that is being collected in our study. It is the output file name of our circuit. In this slide, it illustrates the attack pattern during our experiment. In our setup, H1 is a host, and the left one H3, H6, and so on. The left one is represent the attacker. Each attacker host generate the high volume traffic aim to overwhelm the host. In this slide, we detail the attack pattern used in our experiment. The attack are executed over 20 rounds, with each round consisting of 3 distinct types of DDoS attack performed in each following order. The first one would be the ICMP, and second one is UDP, and then lastly TCP sync file. This the overview of attack traffic data transmission in a single round. Let's start with ICMP, UDP, and TCP, and then continue for the round. This slide we define the key parameter used in generating attack traffic in our study. The attack traffic is controlled by the attack is generated using HPing3 command, which allow us to configure some settings. For protocol setting, yes, we are using the HPing3 to generate attack protocols such as the ICMP, UDP, and TCP, and then the packet size, we set the packet size to 300 bytes for attack traffic. This fixed value ensure the consistency in our experiment. And then transmission interval. The interval between the packet transmission is set using the faster, which is give the interval approximately to about 0.1 millisecond to 1 millisecond.
Okay, so next I will explain the framework for detecting and mitigating network traffic anomaly. So the process begins with the controller monitoring traffic via the OVS switch. As data flow through the network, the controller continuously analyzes traffic pattern for any sign of anomaly. So if it detect as anomalous, the mitigation process will begin by block the affected switch port of the system. So our network traffic anomaly detection model uses a decision tree algorithm that leverages key features to identify anomalies effectively. So the features of our decision tree algorithm consisting of packet count, which show the number of packets that can be early indicator of a DDoS attack. Monitoring this count helps detect sudden traffic spike. Next is byte count. The larger packet size or increased byte count typically indicate higher traffic volume, which could suggest abnormal activity. Third is packet count per second. It reflects the packet count over time, offering a temporal perspective similar to the raw packet count. Fourth is byte count per second. Represent the byte count over time, analogous to the raw byte count but with a time-based ratio. And the last one is IP protocol, which can help identify the protocol type, aiding in the classification and detection of network traffic anomalies. So in the first case study, we will see the effect of UDP and TCP iPerf bandwidth on the classifier model performance. The classifier model performance will reduce. In the next case study, the effect of ICMP packet size on classifier model performance. So in this case, the normal traffic profile is the ICMP packet size are varies of 50, 150, and 250 bytes with a 2 millisecond interval, and also TCP and UDP iPerf bandwidth at 20 megabit per second. So, and also the attacker traffic is the same as previous case study. So in this case, likewise, when we have a lot of traffic from the normal user, the model performance will drop. And the last case study, we will see the effect of ICMP packet interval on classifier model performance. So in this case, the normal traffic profile will be ICMP packet interval values of 1, 2, and 4 milliseconds with the size of 150 bytes and TCP UDP iPerf bandwidth at 20 megabit per second. And for the attacker traffic profile, it will send ICMP packet size of 300 bytes with around 0.1 to 1 millisecond interval. So in this case, when the higher interval of packet can help improve the efficiency of the model because the lower frequency of the packet has been transferred to the system. So in conclusion, when normal user traffic closely resembles attacker traffic, for example, like higher bandwidth or larger packet size, the classifier performance will deteriorate. Conversely, when there is a significant difference between normal user traffic and attack traffic, the classifier will perform more effectively. So once we detect that traffic is anomalous, then we will begin the process of mitigation. So in this case, we will block the switch port to leave that anomalous host out of the system. Here we will evaluate the detection and mitigation algorithm of our system. So in this experiment, we will have server host at host H1 and normal host at host H5 and H11 and attacker host at H9 and H18. And we will monitor the traffic at port 1 of OpenPort switch 1, which is the port of the server host. In the first evaluation, we will send the TCP sync flood attack from the attacker host, which is H9 and H18, to the server host, and also we will send the normal traffic profile, which is TCP iPerf with bandwidth of 10 megabit per second from host H5 and H11 to server host H1. The results show that at first 100 seconds, the mitigation system is not activated yet. So they are consisting of both normal traffic, which is the green line and the purple line, and also the attacker traffic, which is the yellow line and the red line. And once after the mitigation has been activated, the red line and the yellow line has been removed from the system, which means we have successfully blocked the traffic from the attacker host. And next, we will send the UDP FAT to the server host from the same attacker host, and also from the normal host, we will send the UDP iPerf bandwidth of 10 megabit per second. So likewise, before the activation of the mitigation system, the system have to handle both the traffic from normal host and also the attacker host. But after the activation of mitigation system, it will remain only the purple line and the green line, which is the traffic from the normal host. And lastly, we send the ICMP flood to the system, and for the normal host, we will send the ICMP packet size of 50 bytes with 2 millisecond interval. So at first 100 seconds, they are consisting of both attacker host and normal host traffic. But after we activate the mitigation system, we can see that it remains only the normal traffic host. So in this test bed, we we develop our test bed to test the model and also the mitigation system, and we can see that our system can block the attacker traffic from the anomalous host. So that's our work. Thank you very much.
Yes, thank you, Nat and Pachapong, for demonstrating your work on anomaly detection and mitigation system. So, are there any questions? Yes.
Yes.
Thank you so much for your presentation. Actually, I have a question. As you mentioned, the switch port blocking in your flowchart. In your flowchart, I was seeing the switch port blocking. So, is it a reasonable solution to mitigate the DDoS attack? Because if you block the port of your switch, then once we receive any attack, our system will block the port. So, do you think that it's a reasonable solution? If you see your flow chart, in the last of that flow chart, you have block affected switch port. So, after mitigation procedure, you are blocking the port of a switch. So, is it a reasonable solution?
In this case, we block with some predefined time limit. So after that limit of time, then your switch is not blocked anymore, and that port can be used again.
All right, but my question is, if an attacker sends the storm of different DDoS attacks at a single time request, so we block our ports for many times, we hang up problem. For example, we have 24 ports in a switch, and the attacker sends the attacks from different ports. So we block all the ports. So how can we mitigate this system? I think it should be further improved. Rather than blocking a switch, we should see something else to mitigate this problem.
Sorry, can you repeat the question again? There are some connection issue in our side.
All right. So
Could you?
okay, I am going
Sorry.
to repeat. I am going to repeat it. Actually, in your flow chart, I have seen the block affected switch port. So, as my friend is saying that it is for a limited time, and once again, it will be unblocked. But whenever the attacker send different attacks, millions of interest requests or DDoS requests to the switch, so we again and again block our switch ports. In this scenario, if we have millions of DDoS requests to our switch, so we block all the ports of our switch one by one. Is it a reasonable solution? Is it a feasible solution? What do you think about it?
I think that the open flow rules that could be defined in this case to the specified switch to those IP addresses or the source MAC addresses of those suspicious hosts. And in that case, then the port blocking would be more specific to only some sources, but not for everyone, although everyone else connecting to the same port, their traffic would not be blocked.
Actually, these attackers are smarter enough nowadays. So they are not sending the data to a single port. I think it should be improved. Rather than blocking a port, we should think about another solution that can be more effective.
Yeah, I agree. Yes, and that's why yes, this is a starting work ongoing, and one of the aspects that your team is still working on is what if the attacker trying to hide himself by adaptively changing its identity, like the source addresses. In that case, it would be definitely, as you mentioned, right, more challenging to try to keep track of just like catch me if you can scenario, right? Yeah. Thank you very much. I think that's a good idea.
Thank you.
Okay, thank you very much, Nat and Pachapong. Thank you for your teamwork and demonstrating your work and explaining the details. So we move to our second presentation of this session, which is physical presentation, not a virtual one. It's from Dr. Mir Mohammad Suleiman Sarwar from Past National University, Pakistan, and he'll present his work on IBNet Cloud and intent-based augmented reality cloud and overlay network orchestration system with RL-enabled routing.
Bismillah ar-Rahman ar-Rahim. Everyone can hear me. I'm
Yes.
Mir Mohammad Suleiman Sarwar, and working at FAST, and I did my PhD from Jeju National University. I will be presenting my topic, that is IBNet Cloud. Basically, I am presenting an intent-based networking application that is used for deploying clouds at multiple locations remotely in different countries, and then using the same application we deploy an overlay network between them. That network is then used for communication for cloud to cloud. Of course, there could be multiple challenges then in that overlay network, such as path selection for communication, and also in the end I will present an AR application, an augmented reality application that we have developed in the lab. For the path selection, we have used reinforcement learning. I will explain in my presentation. So I will introduce intent-based networking, the problems that we have, some proposed solution, the experimental setup for that proposed solution, then some deployment, how we implemented that system, and at the end I will show some results and conclude with a demonstration. So what is intent-based networking? Intent-based, this is a picture of the complete system. So we have our infrastructure lying below, and then we have a monitoring system that collects the network statistics. Here I must point out that I am collecting network statistics of the overlay network. So I have to connect the monitoring system with that. Actually, the network was established between OpenStack based clouds. So I have to deploy the tunnels between the clouds, and then I have to monitor the network that. So that drives the reinforcement learning model. Of course, since
Recording in progress.
it continuously learns from the model, so I don't need a time series database for storing the data. And then the IBN, that is the central entity, it coordinates with all those modules. It receives intents from the users.
Dr. Suleiman, can you please show us the slides, because we cannot see the slides. There was some disconnection because of some network issue. I think we
Yes,
couldn't see the slides
Can you see it now?
here previously. No, not yet.
I have already given a complete idea of my presentation, though in the next coming slides I will just go in the details of it.
Yes, we can see the slides. You can switch to presentation mode, or maybe you can just.
Can you see now, Dr. Afaf?
Yeah, you can. Yeah, you can switch to duplicate display settings. Go to display settings, and then you can. Yeah, hey, maybe I think it's loading. We just see a black screen now.
We cannot see the other
Yeah,
black screen.
Yeah, it's a black screen. I mean, yeah, we cannot see.
Oh, I think it's coming. PowerPoint is opening up.
Yes. You can switch to presentation mode, please. Yes, we can see now. Yes.
Is it visible now?
Yes. Your slide, but you ended the slide. I think.
Yes. So for the monitoring purpose, there were some configurations required.
There is some issue again, Dr. Suleiman. We cannot see the slides on the main screen.
Can you see it now?
Yeah. It's okay now. Good now.
Okay. Thank you so much. Sorry for the trouble.
Yeah. It's okay. Welcome.
Implement an OpenStack cloud at a server, so there are some default types. The first problem was that if we have to establish an overlay network, so each of the destination switches should have unique IPs for communication. Then having those unique IPs, we can then monitor the traffic from this suppose one source IP to another destination IP. The problem was that the OpenStack had some default IPs. In order to resolve that, we assigned unique IPs to the default bridges of OpenStack, but that actually crashed the internal system, and we had some other issue in OpenStack. In order to solve that, what we did was we introduced a mediator bridge. So the mediator bridge would serve the purpose for communication, and also we can then assign a unique IP to it. So that can be then monitored. And so for the monitoring, we use tools such as OBS Pinger and Node Exporter for having unique IPs for each tunneling endpoint. I want to mention at this point that in particular I use Geneve tunneling because that was supported by OpenStack at that time. So of course we could use VXLAN, but at that particular, in the newer versions, the VXLAN was not actually supported. In the older versions of the OpenStack, VXLAN was supported. So coming towards the reinforcement learning, so this is a networking problem in which we have to do path selection. So I want to bring your attention to the states and actions. So in this particular problem, since we have to do path selection, so each of the node is a state, and the edges, that is the links, that is the tunnels, are actually the actions taken. So if data has to travel in one particular path, so if the data packet is suppose at some node, it will take a link and then it will reach to another node. So these are the states and actions. And here I must identify what type of data we were collecting. So there were two types of metrics that we were considering. One was the network metrics such as round trip time latency, and we were also considering the node performance, that is the CPU. So combining that, we formed the reward matrix. This data from the monitoring tools was actually extracted by an off-platform application. This was our implementation of it, and the IBN could then submit an intent in that particular reward matrix by providing a source and destination. Using reinforcement learning, the path can then be decided. After the path is decided, the IBN then implements that particular path for communication. So this is just a screenshot of some results. Suppose if I want to communicate from node 3 to node 0, I have made a representation of each of these nodes: NUS, PERN, SUD, University of Malaya, Koran-Nok, NCL JNU, and Institute of Technology, Cambodia, but representing them with numbers 0, 1, 2, 3, 4, 5, 6. So we can actually have these states and actions in the reward table here. Graphically representing that, suppose if I want to communicate from node 3 to node 0, suppose from node 3 to node 0, so it then gave me a path. This is the learning curve for it, how it turned. So to conclude my presentation, we present an automated, intelligent, closed-loop and intent-based system for orchestration of multiple clouds and overlay network. This particular system deploys multiple clouds, and then it deploys an overlay network between these clouds. Path selection for communication is done between multiple clouds using reinforcement learning, and then the IBN implements that path for communication. So followed that, there is a small demonstration of the AIR application that was developed.
Without definition to measure signals.
Okay. May I ask question?
Yeah, can you please show the demo on main screen, because we cannot see the demo on the main screen, please.
Can you see it now, Dr. Afaq?
Yes, we can see on the main screen now. Yeah, please, you can continue. You can start. Yeah.
Can you play the video from the beginning, please? Okay, that's it. It's fine. So initially our IBN was a web-based application that later on I turned towards an AIR application, because augmented reality brings the advantages of enhanced usability. It's very easy to deploy tunnels. For example, you have to just tap on two nodes and deploy the tunnel, and it also You can see the network right there. It's the network is easier to understand. So here on the map we are just setting the location of the node that is going to be deployed. I must say these are not exact coordinates, but we have to point on the graphical country. So we had a total of 3 nodes, Pakistan, and then displaying all nodes that were deployed. And also when we hover, we can see the monitoring system. Can you pause here, please? So in our monitoring system, we actually deployed Grafana and such type of tools. So the output window that we see here is actually a browser. It's a 3D browser, but we have set the source to our Grafana dashboard. So the metrics, that is the performance of each node at runtime. So we can just tap on 2 nodes and it will deploy the connections. It was very fast when I was testing it in the lab. Suppose this is an overlay network that was deployed. Now suppose a user is submitting an intent and specifying that he wants to communicate from a particular source to a destination. So the IBN will decide a path for it, and then we can see the path for one particular intent in a different color. So this is a prototype of an AR IBN that we developed. There were multiple suggestions of improving the UI in it. We are still working on it as well. And at the end, just for demonstration purposes, in the video I set the URL of the Grafana dashboard to some YouTube video, just to demonstrate that the window that you see is a 3D browser, just to demonstrate, although this is not required in the project, but to demonstrate. So thank you very much. This was the presentation. Are there any questions, please? Questions, please.
Okay, so in your reinforcement learning operation, so what's your reward function definition?
Sorry, come again. Can you please repeat?
In your reinforcement learning algorithm, what's your reward definition and how can you get it in practice?
I'm sorry, I cannot understand.
He's saying that in reinforcement learning,
yes.
What is your definition of reward and how
Yes,
you're getting
yes,
this
yes,
in practice?
Yes. That is a basic question. Basically, we are considering the cost of the nodes and the cost of the links. So for the cost of the nodes, we are considering CPU, and for the cost of the links, we are considering metrics such as the link metrics such as round trip time latency and other metrics. Thank you.
I mean, comparison with the standard Dijkstra or Bellman-Ford algorithm, was that shortest path?
Actually, in most of the cases it was, but not in all cases. But the reason is that the LSTM, suppose the LSTM and the Dijkstra, if we use that in comparison to select a proactive path, that decides a path based on the data it has. So suppose if the behavior of the network changes, it will still give us the same path unless and until we collect some more data and then we retrain the data. So there could be a study on that, like how to compare with them, that the network behavior changed and now the reinforcement learning is performing better compared to that. But so far, not in this case. Thank you. Yes, sure. Thank you. Thank you so much.
Thank you, Dr. Suleiman, for your nice presentation.
Thank you.
Followed by some nice animations. Yeah.
Thank you so much.
So with this, we move to our final presentation of AI in WG working group, and this is by Sajid Alam from Jeju National University, South Korea. He'll present his work on intent-based resource orchestration in space air-ground networks using graph neural networks and deep reinforcement learning. And this is also a physical presentation.
Dr. Fak, can you please just share the slides?
Your slides?
Yeah. I emailed.
Okay, let me check. You can see now?
Yeah.
The slides? Yeah, I'll switch to a presentation mode, but then I would have to control. Should I control from here?
Just wait a second. Can I,
or should I
operate from here?
I'm not sure because I have the control, so you will not be able to control from there. Or I can send the file maybe in chat if it's possible.
Can I email? Hello everyone, my name is Sajid Alam. I'm a student of Professor Song, working under his supervision. I'm doing my PhD in Jeju National University. The presentation presented by the Dr. Mir. He's our senior lab member. He graduated from NCL lab as well. So today I will present the IBN-based Sajin network. Actually, our lab from last 3 to 4 years continuously working in the IBN system, and we are trying to integrate IBN system in multiple domains. So recently we got the project about the space, air, ground integrated network. So our aim is to integrate the IBM system to the Sajin network. These are the outlines of my today's presentation. First of all, I will explain about the Jeju Island special case for the satellites companies. That why a lot of companies they are approaching to the Jeju Island, and then I will explain about what is Sajin, and then I will describe about the intent-based networking and how we can integrate the IBM system into the Sajin network, and then I will propose my solution. Actually, as you can see, this in the left side, there's a small dot you can see here. You can see there that there is a small portion of the Jeju Island. So actually, a lot of companies they are approaching to this place because of some specific advantages that island has. If I talk about the location, it based on the East Asia. So the advantage of this island is to receiving and sending commands to the satellites, because it has a very minimal obstacles if we talk about to communicate with the satellites, because there is very less number of buildings, and there is only one big mountain, which is the Halasan. So that's why it has the specific like view of direct line of sight angle that it transfer the data from ground station to the satellite, and then it based on the surrounded by very big oceans. So that's why it's a good place to most of the satellite companies. They are trying to make their base stations in the island, in this island. So one of the Korean company, this is the name is the Contact. They already deployed their ground station in this Jeju Island, and they recently launched their small pod of satellite with the SpaceX company. So as the number of satellites ground station in Jeju Island increasing in the future, and it is necessary to analyze the performance of satellites communication links in sub-ideal information environment such as radio interference, and the further research